Hello, and welcome to another Math with Taebyn. My name is Taebyn. I'm the pup Bark. Today, in this video, I want to do part 2. So, I did part 1 video. I'll put a link in the description to looking at the geometry of eigenvalues and eigenvectors in linear algebra. So, in that video, I focused on not computing them, but actually looking at geometrically what's happening with these things. So go back if you haven't already, take a look at that video. And I talk about the general things that are going on in 2 dimensions. In part 2, I want to do an example, this example right here, computing, not really computing, but finding the eigenvalues and eigenvectors of this particular transformation without using the definition, but by using the ideas of what's happening geometrically. And this is really fun and cool and can be very useful to do. In general, it can be useful to understand the geometry of what's going on, because that can help you figure stuff out. Woo! Okay, I'm excited. I'm so excited. Are you excited? Oh, I'm so excited. Okay, in this video, I just assumed that you remember the definition of an eigenvalue and eigenvector, which is right there. And in the other video, we saw that for this particular vector, where v ends up, wherever, go back to the video, I brought pictures, but wherever it ends up, it lies on the same line through v. If lambda is a real number, we'll focus on real numbers in this case. So if lambda lies on same line through v, if lambda is a real number. So remember that idea. We'll use that idea to help us figure out what the eigenvalues and eigenvectors of this particular linear transformation is. Oh, and that's exactly, wow. One's changed color. How about pink? I like pink, because then we can get this party started. That's why we like pink. Okay. Anyway, still, what we have here is a plane flying around. Maybe like that. Represent that by capital pi. Let's think here. So if we're going to be a real eigenvalue, it's going to correspond to a vector that after I do the transformation, in this case reflecting over the plane, it should end up on the same line. Let's just look at any generic vector and see what would happen. If I take any old vector, that's supposed to be an arrow, use your imagination. If I reflect it over the plane, where does it end up? Where does it end up indeed? Well, if I reflect it, it ends up down here, right? If that's what I wrote. It does not end on the same line through v, because that line is right, well, you see what I'm trying to do, is right there. It doesn't lie on that line. Okay, so we're looking for a vector so that when we reflect it over the plane, we end up on the same line. So let me get rid of this, because that doesn't work. Just like me on a weekend or any other time. What if I'm perpendicular to the plane? What exactly? If I'm perpendicular to the plane, so that is a 90-degree angle right here. If I reflect it over the plane, where do I end up? I end up pointing just directly down. Well, as I found the picture. That lies on the same line through the original vector. That tells us that any vector perpendicular to the plane is an eigenvector. Wow! Notice, when I've reflected it, it's the same length in the opposite direction. So notice this. We can just look from the geometry that this equals negative v. That's a -1. So any vector perpendicular to the plane is an eigenvector corresponding to the eigenvalue of -1. So there's infinitely many. You might remember this from your studies in linear algebra and eigenvectors, eigenvalues, that you never have just one eigenvector. You have infinitely many, any scalar multiple of an vector is another eigenvector, but we can just choose one. We only look for linearly independent eigenvectors is typically what we look for. Now, if you remember, so this should probably be in the assumes you remember, but if you remember from, well, you probably learned in vector calculus or multivariable calculus, you can read off vector that's perpendicular to any plane from the coefficients. Note that the vector, I'm going to write it in column form. You might be used to it in horizontal form with the angle brackets. But so this is the same as the vector you might be used to writing it like this. 1, 2, 3. Anyway, this vector is an eigenvector corresponding to -1. So V equals 1, 2, 3. And any scalar multiple. And any scalar multiple. Now, so that's what a situation. We're close now. We've almost got them all. What's the only other case we have not considered? We've considered the general case. We've considered perpendicular. What about a vector in the plane? Well, now if I reflect it over the plane, but I'm in the plane, where does it go? It doesn't go anywhere. Crazy. So it actually stays there. It stays fixed, as we say in math. So we can see by the geometry that it doesn't move anywhere. So we have that for this vector. So for any vector in the plane, I'll just write it, V in the plane, it doesn't move anywhere. So that allows us to write down the equation T of V equals V. Oh, but there's an invisible 1 right there. So what's the eigenvalue? It's got to be 1. I'll put corresponding to the eigenvalue 1. So just like before, the geometry allowed us to compute an eigenvector. Knowing this, we can now still also compute eigenvectors corresponding to the eigenvalue 1. So let's do that really quick. So hopefully you have it. We don't really need the picture right now. We just need that if V is in the plane, then T of V equals V. And so then we found our eigenvalue equal to 1. So now we want to compute these eigenvectors. Well, if V is in the plane, it has to satisfy the equation of the plane. So if V is in the plane, we know that this is true of the coordinates. I'm going to solve for x, and you'll see why in a second, because we want to be able to represent any general vector V. So I'm going to, if I subtract 2y from both sides, and then subtract 3z from both sides, I see that whatever the vector is, so I'll write it in this form. What I'm going to do here, you might have seen earlier in your linear algebra course, but it's a very useful way to break up vectors and find linearly independent vectors. Side note. So any vector, we know that the x component looks like this. And then the y component is just whatever it wants to be. It could be a fireman, it could be a truck, And same thing with z. Now, notice, I can break this up into, I'm going to separate the y's from the z's, because I'm wise like that. So I can write this as -2y, y, and 0. So let me finish writing this. You can see plus, then I have -3z. Then I've already taken care of the y, so this is 0. And then I have z. Do you see how I broke that up like that? If you have any questions, leave a comment in the description. But if you add these two vectors, you can see that you get the same thing. So I've just rewritten it. The reason I did this was because now I want to factor out the vectors, basically. So I can rewrite this as, if I take out a y, we might have -2, 1, 0. And then if I take out a z, we're almost done here. This is exciting. I get -3, 0, 1. So nth eigenvector corresponding to 1 is a linear combination of these two vectors. And these, you can even check, these two are linearly independent. I'll just signify that by saying that, writing it all out, I'll just say these two are linearly independent eigenvectors corresponding to 1, to the eigenvalue 1. These two turn out to be linearly independent to that other one we found, the one that's perpendicular. So we have 3 linearly independent eigenvectors, and we found all the eigenvectors and all the eigenvalues with just understanding the geometry of the situation. And this is really cool and fun, and I really like this idea. I hope you've learned from it. I hope you had a lot of good time with it. As I say, if you have any questions, leave them in the comments below. Other than that, I'll see you next time on Math with Taebyn.